Well, welcome everybody. Good afternoon, good morning, good evening, however it may be. These virtual seminars are a great opportunity to bring together people from all over the world, so welcome. It's very exciting, and I'm very grateful to have been given the opportunity to talk to you today about structural equation modeling. In particular, thanks to Jody and the EFI, Dennis and Krishna and Vianney from the Ecological Society of America. They reached out, and I was very happy to put together this presentation for you. And some example code that we'll walk through. So as Dennis mentioned, I work for a program at the Smithsonian Institution called Marine Geo. This stands for the Marine Global Earth Observatory. We're a network of scientists, researchers, volunteers across the globe interested in understanding how coastal ecosystems work and how to keep them working. And so I mentioned that by way of saying that I'm not a classically trained statistician or mathematician. I'm a community ecologist, I presume, like many of you. And so I use that as background to say that I came to structural equation modeling during my graduate career. It was actually my PhD advisor who gave me Jim Grace's 2006 book on the topic and was evangelizing me. And of course, I'd taken my first year statistics course at the time, and I thought, well, what's all this? It looks complicated. I can run an ANOVA. I can run an LM. That's all I need. But I think it was through the research that I've done and am doing currently that I recognize the value that this network approach to understanding natural systems, the benefits that it can impart to both our understanding and, of course, then for our forecasting and the other measures that Jody mentioned. And SEM is kind of interesting because it is a statistical machinery, but it's also kind of a philosophy. And it really makes you think deeply about what you know or what you think you know about your chosen study system, and being very thoughtful in how you put together your questions, your hypotheses, and ultimately your model. So what we're going to do first here is kind of walk through a bit of this background about structural equation modeling and a little bit of the history. And then we'll dig into some of the machinery and the mechanics. We'll do a worked example in R, and then hopefully you will come away inspired to be able to use structural equation modeling for your own questions. So this should look familiar to a lot of you. I don't know if we could do this, but anybody who works in like a grassland system like this, just want to give a thumbs up in the Zoom. I see 2 participants, hands raising. I figured as much. Yeah, I'm seeing floods of thumbs up. So that's good. I mean, grassland systems have been central to progressing our understanding of ecology for many decades now. Some of the topics that I'm interested in were first pioneered in grassland systems. As you can see behind me, I was so inspired that I decided to study the marine equivalent seagrasses for my career. And it's been since the 70s or so that there have been some central questions that have emerged from our investigation of grassland systems. For example, how does resource availability influence the composition and diversity of the plant community? Generally through our understanding of things like competition and resource limitation and maybe even stress gradients. There's been lots of course, experiments and observations trying to link these 2 properties together. And from a statistical vantage point, it can be quite easy to investigate this relationship, particularly if you're working in a controlled experimental system like you see in the background. And you might be compelled to fit a simple regression like the one that you see here, where you're attempting to predict the variation in diversity as a consequence of the variation in whatever resources that you're looking at. But in recent times, well, not so recent anymore, actually, since the 1990s, there's been another question that's emerged and become central in our study of grassland systems and indeed beyond, which is how the resident diversity influences what we would call ecosystem function. So this could be things like biomass production or nutrient cycling or decomposition. And so you can see as we branch out in our understanding of these systems, that now there's a bit of a flow of information from the resources to the diversity to the function. And in the past, we might have fit a multiple regression like this, again, predicting variation in some function like productivity as a consequence of variation in diversity and resources. But this isn't really reflecting the diagram below, because we have this potentially indirect pathway between resources and function that is what we call mediated by diversity. So our statistical package, our toolbox, if you will, might not be fully equipped yet to be able to disentangle these so-called direct and indirect effects. And of course, under controlled experimental conditions, it's easy to manipulate things like diversity in resources. We can add fertilizer, we can remove species. But ultimately, we want to understand what are the consequences of variation in these properties for whole systems that may be untractable to manipulate. And in this case, then, we might additionally consider the role of abiotic environments, so gradients in things like temperature and precipitation and elevation or salinity, if you are more marine-oriented, in influencing actually all of the variables that we measure in our ecological communities. So if we step back, we had a very focused question originally, and we've managed to build out this whole network of hypotheses about how all these variables are interrelated and how they might be influenced by and ultimately lead to, say, functioning of ecosystems controlled by the abiotic environment. And that's where structural equation modeling steps in. This is a tool that allows us to take these multifaceted hypotheses, these networks of causes and effects, and actually fit statistical models to them in a way that we can evaluate the entirety of this network at once and actually test multiple hypotheses simultaneously. So that brings us to structural equation modeling. And I thought it'd be valuable to break down this term so that we're kind of all on the same page as to what each of these individual words mean in this phrase. So structural implies that there's some underlying structure to nature, a cause and effect. We are just observers, but there are processes out there operating in nature that we are trying to measure. And we think we know how they're related. So we can, again, put together this hypothesized network that reflects our understanding of what we believe that structure to look like. Then we can translate these paths, if you will, into separate equations that we can then fit to data to support or refute the proposed structure. So as I mentioned, SEM, or structural equation modeling, is kind of this interesting intersection between scientific design and philosophy and actual statistical methods, in that you have to have some understanding of that structure in order to derive the equations, collect the data, and ultimately model the outcome. So that's what structural equation modeling is in a nutshell. It's a series of equations that are united in a single causal network. And we can investigate the flow effects through a system, like I mentioned, those indirect effects, which is one of the major benefits of the application of SEM. We can disentangle how resources might flow through something like diversity to impact functioning, or how resources impact functioning directly, and therefore get a more nuanced and mechanistic understanding of how these systems are working. But you'll notice here that I've said that these variables are united in a single causal network, which raises the idea of what the bleep is causality. And this is an incredibly complicated question, and one that's far beyond the confines of this talk. I would actually wager that I'm still trying to wrap my brain around what causality means, both in terms of its definition, but also its potential application. But it is important to point out that we are implicitly assuming that those pathways, the flow of causes and effects throughout our model, don't represent simple associations. That in fact, that if we to tweak, say, resources, that there would be an actual consequence for diversity. And that's something that we're going to have to swallow if we wish to apply SEM. And that's difficult, because if you're like me and you've taken an introductory statistics course during your graduate school or during your undergrad or elsewhere, you probably heard this popular mantra that correlation does not imply causation. You can find a statistically significant association between two variables, but that doesn't necessarily mean that one causes the other. And I'm actually here to tell you today that this is not true. And I'll use a quote from a book that came out almost 20 years ago now by Bill Shipley called Cause and Correlation in Biology, where he introduces a lot of the principles of structured equation modeling. And in it, Bill writes, in fact, with few exceptions, correlation does imply causation. A simple correlation implies an unresolved causal structure, since we cannot know which is the cause, which is the effect, or even if both are common effects of some third unmeasured variable. So in fact, this statistical correlation may represent causality, but it's up to us as the investigators to ask and be able to test with data whether, for example, A causes B causes A, or A and B are both being driven by some external factor that influences both of them such that they would appear to be correlated, or what we might think of as a spurious correlation, or in the parlance of SEM, a correlated error. And I would say, again, we all grapple with this notion of causality. I found this tweet a couple of weeks ago that I thought was pretty relevant. Major causal inference issues in our house. 2-year-old thinks coats make the air colder, so keeps putting on hers when she's too hot. So how do we design a model that actually gets at these causal implications? And there's a lot of ways we have been doing this, and a lot of ways we can continue to do this. The first is designing and conducting controlled experiments. This, of course, is the gold standard. We've recognized for a century in ecology that controlled experiments are the most efficient way to be able to understand cause and effect. You know, if you're interested in the effect of resources on diversity, you can do that in a greenhouse where you can control all these external factors like soil composition, temperature, humidity, and remove those potentially confounding influences that might drive those spurious associations. We can also lean on our deep understanding of ecological theory to help us inform the directionality of effects, or can even use simple logic. And I use the example of an SEM that we fit to some data here in the Chesapeake Bay in the United States, where we were interested in how land use change influenced water quality parameters, so the waterways, the rivers and streams associated with the bay, and then ultimately how those effects trickled down and influenced the underwater vegetation. And we made the logical argument that, say, for example, fertilizer application by farmers in their field is those nutrients are driven into the waterways through runoff, and those change the water chemistry. It is in fact the other way around, in which our streams and rivers spit up nitrogen and phosphorus that lands on farmers' fields. So we can use some of this deduction and these theoretical constraints to help us hone in on the directionality of our effects. And of course, we can build knowledge from past observation. If we think about the little girl putting on her coat, she might realize eventually that putting it on does not, in fact, make the temperatures cooler, but rather she just gets hotter and hotter. And we can then test these hypotheses by collecting data, by conducting experiments, by making observations. We can continue to build that knowledge, advance theory, and ultimately progress towards a better causal understanding of ecological systems. And here's a quote actually from almost 100 years ago by Sewell Wright, who was the pioneer of the first generation of SEM, basically asserting the acceptability of inferring causality with SEM. It's the combination of knowledge of correlations with knowledge of causal relationships. We're not simply relying on the statistical correlation to tell us there is a causal relationship, but in fact, we are imposing our understanding of causality on that association. So if we then develop our understanding of these potentially causal relationships, and we can build, say, the path diagram on the right that reflects at least our current understanding, how do we then go about fitting a structural equation model? So the first is to, again, build this hypothesized causal structure. This is not necessarily set in stone, which is to say that we are constantly learning and that we may reevaluate either through the presence of new information or the outcome of our analysis and revise this causal structure iteratively. Of course, that is how science progresses. So once we have this causal structure, we can collect the data, again, through experiments or observation. And then what we want to do is test that data against the hypothesized structure and ask whether or not the data support the relationships that we've specified in our path diagram. And if they do, we can extract our inferences and go on to talk about, say, how birds influence barnacles and how those are also influenced by tidal height and so on and so on. If we fail, or rather, if the data fail to agree with our model, it's probably because our model is wrong. So as I say, we can go back and refine the model based on new information, based on associations that may have come out in the data that maybe we hadn't considered previously, maybe that we thought were unimportant, but which the data might be suggesting to us, hey, there's something going on here. It may not be causal, and that will require us to dig a little bit deeper, maybe collect some additional data, but it's a good warning flag that at least our original hypothesis is likely not to be correct. And I mentioned these things like path diagram, box and arrow diagrams. This is a sort of graphical tool that we use to be able to reflect these causal relationships and build them out to create our hypothesized causal network. And so we're all familiar with the graphical depiction that you see here, a simple bivariate plot with a regression line, which we can express, of course, mathematically using the following notation. Or if you're into SEM, you might prefer some slightly modified notation. But ultimately, what we do is then take those equations and retranslate them into a new graphical form, in this case, in the form of boxes and arrows. So here we have a relationship or a correlation between x1 and y1. But instead of just having that bivariate plot, we actually have the arrow leading from one to the other, which is alerting you, the reader, that we expect this to be unidirectional. In other words, a cause and an effect. And so we'll move through the rest of the presentation using this graphical notation. I hope that it's familiar to you. At least it should be familiar. It's a pretty intuitive way to build out our knowledge and understanding of systems. And I'll show you some examples in just a second. But I did want to call attention to this. This is a path diagram made not of boxes and arrows, but actually delicious baked goods that represent somebody's thesis that they posted on Twitter. So I just want to say, fantastic work. This is the best path diagram I've ever seen in real life. And you get the Hollywood handshake. But I mentioned earlier that it should be reasonably intuitive for us to interpret these box and arrow diagrams. And in fact, we have been doing this for some time. Here's just a couple of examples from classical studies and works that you ideally are familiar with that utilize these box and arrow diagrams. They're very intuitive. They serve several purposes. They allow us to express the entirety of our hypothesis in a single graphical depiction. That's very cool. It also allows us to embed our knowledge into and our understanding of the field as a whole into these central questions. And finally, it is a tool to report the outcome of our actual fitting of mathematical equations, which we'll show you an example of here coming up. So by way of background, there's been several iterations of SEM. The technique itself is about a century old now. The very first generation SEM, which, as I mentioned, was pioneered by Sewell Wright and his colleagues in the 1920s, which is otherwise referred to as path analysis, looks largely at variables that are observable. This is in contrast to the second generation SEM, which combines this path analysis with something called factor analysis. So you may have heard reference to things like confirmatory factor analysis or latent variable modeling. These are variables for which we can measure indicators, but we might not be able to measure directly. So the classic example is, say, intelligence. We have an intuitive understanding of what it means to be intelligent, and we can measure indicators of intelligence. We can give people tests and see how they score, but we can't really measure intelligence directly. even though this is an important variable in social sciences and one which we would want to include in some of our statistical models to predict all manner of things like income, education, and so on. And in this case, the combination of path analysis and factor analysis in the 1950s allowed us to do that. And this was united under the umbrella of what we'd call global estimation. So this takes that entire network, like I had shown you previously, and creates a single global variance covariance matrix, of which then the model attempts to reproduce those correlations by generating path coefficients, what we might consider betas, say from a traditional linear model, and again, use that as a path towards evaluating whether the data fit the model and then what these actual relationships look like, their direction and magnitude. And for those who have done this before, who have heard of SEM, they may have heard about it as implemented in the Lavon package, which stands for latent variable analysis, hence the implication of factor analysis and path analysis, again, constraining towards this single global variance covariance matrix and its estimation. And finally, we come to the third generation of SEM, which is heavily informed by graph theory. And in fact, there's lots of really fascinating resources out there which link causality and the development of these path diagrams and how one might actually at least become closer to inferring causality through some basic principles. And again, not enough time to go over them today, but it's really worth looking at, especially if you're thinking about building your own models. How can you better develop a path diagram to infer causality using these graph theoretic principles? So I can provide some background if anybody, or reading materials if anybody's interested. The major departure from this third generation of SEM is that instead of estimating this single global matrix that includes all the variables at once, it actually estimates each equation individually. And so it's somewhat less elegant in that sense, but it vastly increases the flexibility of the method because every equation can have different assumptions, different error distributions, different fitting functions. And often in ecology, those are the kinds of messy data that we're dealing with. So here, this third generation SEM is far better equipped to accommodate the kinds of data that we're working with. And this, of course, is done through the piecewiseSEM package, which I developed several years ago now. It's very flattering to hear that it's being so widely used. It also makes me horribly nervous because, as with any package, it's rife with bugs. So hopefully most of the functionality is there. I will say this again at the end, but please feel free to reach out if you do run into any issues. I do my very best to try to get back to everyone who does contact me. So we're going to focus here on the application of the piecewiseSEM package, in particular, how one may go about actually coding within it, developing these structural models, and then extracting inferences and making some interpretive statements. And to do that, of course, we're going to go to R. And so before we do that, I just want to give background on the data set that we happen to be working with today. This is an example data set that's been used in a wide number of lectures. If you've ever taken Jim Grace's workshop at the ESA meetings, I believe he uses this, the data set that I'm about to speak of in his lectures. And of course, I use them in mine, my colleague Jarrett Burns in his. So it may already be very familiar to you. The benefit is that the data are already included in the package. So really, there's nothing to download, nothing to import. We should have everything we need as long as we have piecewiseSEM installed. And that data set actually comes from a paper by Grace and Keeley from 2006, which basically was trying to understand how does fire severity influence California shrublands. So they identified 99 sites, which they measured pre and post fire for various kinds of abiotic and biotic characteristics, including aspects of temperature, soil properties, and then, of course, the ecological community itself, so composition, biomass, diversity, and so on. I'm going to put aside the fire severity component here for the time being and just focus on the plant community metrics, although the paper, which actually does implement SEM, has a much more complicated analysis than I will present here. Obviously, for this introductory lecture, we're going to want to kind of try to keep it simple, but it's a good demonstration of how complicated these models can get and still be fit and still provide interesting insight. And so here is that simplified model that we'll be evaluating using the piecewise-SEM package. In this case, we have 4 variables that have been measured and reported in the 2006 paper. The first one on the left here is the distance from the coast. So they had a gradient from the shore to inland. They hypothesized that this distance would influence both the abiotic conditions, for example, soil nitrogen concentration, but also the composition of the ecological communities, so the spatial heterogeneity and species composition. So they computed a metric to be able to report the degree of heterogeneity there. And then ultimately, the abiotic conditions and the species composition would both influence the species richness, the number of different species that were found in each of these plots. And so this is going to be the initial hypothesis that we are going to, or I should say, set of hypotheses that we are going to evaluate using the piecewise-SEM package. And we're going to do that in a couple of steps. The first is to create a list of structured equations. So we're going to take these box and arrow diagrams and back out the mathematical equations so that we can code them in R. This can be somewhat of an art, particularly if you have a very large and complicated diagram, but it is necessary and important to be able to do properly. Everything that comes after depends on the proper specification of the models. Then we're going to evaluate whether the data that have been collected support or refute this particular hypothesized structure. We're going to do that in 2 different ways. We're going to perform something called the tests of directed separation. This, again, comes from graph theory, but basically asks whether or not we are missing any important relationships that are implied by our data within this specified causal structure. The other way we're going to do it is a new method that was just published recently by Bob Duma and Bill Shipley, where we look at the likelihood of this model relative to a model that includes those missing relationships. And we'll elaborate a bit on that when we get to it in just a few slides. And finally, if we're happy with the model, we're going to extract the path coefficients, those betas from the linear regressions, and parameterize this model so that we can begin to draw some inference. So, step 1, create a list of structured equations. In this case here, we have what we would call 3 response or endogenous variables. They are abiotic, hetero, and richness. You can identify these because they're the boxes that the arrows are going into. So in this case, we would have 3 structural equations. One here for abiotic, which is being predicted only by distance from shore. Another for compositional heterogeneity, or hetero, that is also being predicted by distance from shore. And finally, a multiple regression in which we are predicting plot level richness as a function of both the abiotic conditions and the compositional heterogeneity. I would point out that sometimes it's tempting to actually break every path down into a separate regression. For example, richness against abiotic and a separate equation for richness against hetero. However, we really want to include both in the same model because those path coefficients will reflect the independent, ideally, effects of, say, abiotic conditions on richness given a certain level of compositional heterogeneity. And so it's important to be able to code those in the same model so that we can arrive at those estimates that are independent. And then I mentioned that we're going to evaluate the fit of the model. So we're going to take the data that we've collected, or I should say Grace and Keeley collected, and we're going to fit those equations. And then we're going to ask whether or not our hypothesized structure matches the relationships implied by the data. And the way we're going to do that is we're going to actually develop a model in which we test the significance of the missing paths. So one assumption we make in this model is that the relationship between, say, distance from shore and species richness has a correlation of 0. And we also assume that the relationship between compositional heterogeneity in the abiotic environment also has no association. In other words, we don't believe that there's a causal link between these variables. And if this is true, then the data, the correlation or the association that we measure from the data should be no different than 0. If we don't find this, if, say, these relationships are actually statistically significant and different from 0, then we might infer that our original hypothesis is incorrect. And in fact, we might want to revisit this model to include those relationships if we think they are justified. And finally, we can combine the significant tests of those missing paths into a single statistic, a Fisher's C statistic, which will then allow us to compute a goodness of fit for the entirety of the model. So we're actually going to get 2 pieces of information from these so-called DCEP tests. We're going to get the significance of these missing pathways, and this could be really important diagnostic information if we then choose to go back and refit this model with a different structure. And then we're also going to get a global C statistic and a global p-value for the entirety of the model that will tell us whether or not we can support or refute our hypothesized structure based on our data. So this is where we're going to, one minor point too. I would just like to point out that in this case, we're assuming that the missing relationship is between compositional heterogeneity and abiotic conditions. We might equally assume that it goes in the other direction. And in fact, while the parameter estimates will be different in each of these models, the significant tests are symmetrical regardless. So it really doesn't matter which way we fit it in terms of evaluating model fit, with one caveat, which is if either of these data are not normally distributed and may be transformed via link function through, say, a generalized linear model, that will generate a unique case in which the package will actually walk you through the steps to be able to resolve how to fit these so-called independence claims and choose a path forward in evaluating your model fit. We won't get into that in this demonstration, but I did want to make you aware that this can be an issue. And again, the package will identify it for you and be able to ideally easily walk you through steps to resolve it. So in this case, I'd like to stop, switch over to R, and actually do a bit of coding so that we can fit the structural model that I showed you from the Keeley data. And in order to do that, as I mentioned, we're going to use the piecewiseSEM package. I'm happy to say I spent this weekend implementing some new functionality, squashing some bugs. And so if we load it here, just thinking, you'll see that the development version on GitHub is now 2.3.
John, you haven't switched to R.
Oh, okay.
We still see your PowerPoint.
All right. I'm going to do this. I'm going to stop share. I'm going to screen share again. And now you should see R.
Yes, great.
Perfect. All right. So as I mentioned, this is a new version that I'm hoping to push to CRAN soon that will ideally fix some issues that folks have been having. Thank you for your patience. This is a bit of a side hustle for me, so I do try to work on it as often as I can, but it does often take a little while longer than I anticipate to get everything running smoothly. And as I mentioned, the data set that we're working is from Grace and Keeley, and that those data are actually included in the package, which is really handy. And we can take a look at that right now. And we can see that distance from shore, the abiotic environment, this index of compositional heterogeneity, and species richness of the plots, the 99 different plots, are all included here, in addition to some other variables that fit in with their larger questions about fire severity. Again, we're going to ignore those just for the sake of a more simplified example. So, as I mentioned, the first step is to fit the individual structural models that we've backed out from our path diagram, and we've identified 3. The first is between abiotic environments and distance. And in this case, we can code it just as a simple linear regression using the Keeley data. And hopefully most, if not all of you, are familiar with both R and the base functions within R. LM here stands for linear model. If not, again, we can provide some excellent resources to get you up to speed. But the point is that we can fit these using the tools that already exist within the base R software, which is pretty cool. Next, we have the compositional heterogeneity, which is in that original diagram, simply a function of distance. And then finally, we're modeling richness, which, if you recall, was predicted by both abiotic and hetero. So we will now have a multiple regression here. Sorry, that was coded as rich. So that's it. Those are our list of structural equations. And now we would like to wrap them up into a single SEM. And we can do that very easily using this function, pieceSEM, for piecewiseSEM. And we can simply pass along those model objects to that function, and it will fit the SEM for us, which is brilliant. So if we look at this object now in R, it tells us what our structural equations are. This is helpful just to make sure that you've actually broken down your path diagram correctly. So it's always good to double check. And it'll give us a little snippet of the data just to make sure that we're fitting the proper data frame to our equations. It's important to note here that this function can actually accept the models within it as well. So I will very quickly do this here. And will give us the same thing. So either or, you can fit the models outside of the pieceSEM function in the event that you, say, want to do some tweaking on each of the individual models, or maybe they take a long time to run. That can be helpful, or you can just supply them directly to the function as well. I should note that there's an additional argument here, which we can specify to the pieceSEM function, the data set we're working with. The function itself actually dissects each of the model statements and reassembles the data frame from those. However, for certain packages and model classes, this can be a little bit troublesome. And so if you ever run into any issues, say with fitting this model, sometimes it can be helpful to simply supply the full data frame directly using the data argument in the pieceSEM function, and hopefully that will fix it. So we have our model, and now we want to evaluate the fit. And in this case, we have these missing paths that we will summarize in our tests of directed separation. So if we go back to our PowerPoint, we're missing two paths. One is the path between distance and richness, and the other is between abiotic and hetero, or vice versa. And if you remember, I mentioned the way we do this is we actually fit these regressions and extract the significance of these missing paths to ask whether they are different from zero. And then we summarize that information in that single Fisher's C statistic. So in this case, there are two independence claims. Again, we're assessing whether these variables are truly statistically independent, aka their correlation is zero. The first one is between abiotic and hetero. And the second one is between richness and distance. However, I would point out that we actually have paths that are predicting richness in our model already. And as I mentioned, it's important that these coefficients reflect the independent effects. And so what we really want to understand is whether there is a relationship, a statistically significant relationship between distance and richness, given the already specified paths or influences by abiotic and hetero. And actually the same goes for abiotic and hetero. We want to know whether they are statistically significantly correlated given the known influence of distance on both of them. So in this case, we would want to add those covariates to our evaluations of the independence claims. keep doing this, sorry. Now, this is a reasonably simple model, which is to say there's really only kind of two levels. If you start to build out more complicated models, say richness goes on to influence biomass, there are some tips for how far back you go in terms of including these covariates. It's really only the immediate predecessor, because what we're assuming is that the influence of distance is already reflected in variation in abiotic. If we were then going on to imagine how it influences more downstream variables. This can get a bit confusing. So again, I'll provide a resource at the end that will help you walk through how to construct these independence claims specifically. And you will not be surprised to find out that actually the package will do it for you automatically. But it's always good to understand exactly what's going on when you're doing these modeling exercises. So in this case, we can go ahead and look at the output of our independence claims. And in fact, hetero has no significant relationship with abiotic. That was our first claim with a p-value of 0.187, implying that the correlation or the relationship between the two is not statistically different from 0. However, if we look at the second independence claim, we can see that, in fact, given the known influences of abiotic and hetero, there is a statistically significant relationship between distance and richness. So in our model, it's this path here that is suggested to be actually different than 0. And because I realize we're running out of time a little bit, I'm going to skip ahead here and just say that we can combine this information using that equation that I showed you to calculate this Fisher-C statistic. And in fact, here we get a model-wide p-value of 0. So this can be a bit tricky to interpret. Generally speaking, when we have a low p-value, we tend to think things are significant, and we go on to talk about them. In this case, it implies that the hypothesized structure is statistically significantly different than the structure implied by our data. So in this case, a low p-value is actually bad. It says that our model doesn't match the associations that are implied by our data. And in fact, we know from the tests of directed separation that it is this path, the one between distance and richness, that is potentially driving this poor fit. And we can do some soul searching and we can decide, okay, maybe it makes sense. Maybe there's a gradient from inshore to offshore, from the shoreline inland that actually would influence richness. We just didn't think of it before, but we can add that back into our model. And in fact, now if we look at our Fisher-C statistic, we see that the p-value is 0.187. In this case, the model is not significantly different than the relationships implied by the data. So in this case, we would feel okay going on to be able to extract information from the model and make some inferences about this system. Let me just see where we want to go next. Right. So again, the inferential engine of SEM are these path coefficients, which you can see here. These are the linear estimates or the betas from each of these individual regressions. So these are the raw estimates here in the estimate column. So for every 1, say, kilometer increase in distance, you would expect a 0.3 or 0.40 change in their index of the abiotic environment. And of course, you have standard errors and p-values associated with those. So all of these paths end up being significant. I will point out that there's a final column here, which may be unfamiliar to those of you who are coming from more of a LM world, called the standardized estimate. So this actually takes this raw coefficient and scales it by the ratio of standard deviation between, in this case, distance and the abiotic index. And the value there is that the units of that coefficient are now, actually it is unitless, it is in standard deviations of the mean, so that you can actually compare the magnitude of the standardized estimates among pathways for variables that may be measured in very different units. So this is a really important tool, both for being able to talk about the significance and the magnitude of the effects of each of these paths. But also one of the bonuses of SEM is that you can multiply these coefficients in adjacent pathways to be able to calculate the magnitude of that indirect effect as you follow the flow of information through your network. So this can be both a powerful comparative tool, but also one that allows you to extract more interesting information from your network. And I'll point out here that we can also plot the output of this model with the standardized coefficients. It's taking just a moment. There we go. This is using some internal, well, this is using a package diagrammer in the R environment, in which case we managed to produce a somewhat rudimentary path diagram relating the output from our model into this graphical format. I often get the question, how do you visualize your path diagrams? I actually honestly often just use PowerPoint. Other people use Photoshop or Illustrator or Inkscape or free alternatives. The point is that R is not very smart about how it arranges these boxes, whereas we might decide as scientists that we want something like resources to be at the basal level, and we would want a graph that maybe depicts a more realistic structure, a hierarchy with respect to the system than just sort of this automated equal spacing among all boxes that R produces. So I would suggest that the plotting function is a nice way to look at your model quickly in R. For publication-worthy figures, again, refer back to some of these other programs with doing some manual input. So we managed to walk through all of this largely by hand. We've fit our model. We have extracted our independence claims. We have evaluated the model fit. We've updated our model. And then we've taken our coefficients and put them onto our path diagram. This is a bit cumbersome in the sense that we've broken down all these steps simply for educational purposes. You'll be happy to know that there is actually a function like any other model function, summary, where we can actually get all that information in one go. And in this case, summary will give us, again, the call, which is, again, the list of structural equations. Always good to just double check. You do get an AIC value, which is really important to be able to make comparisons among competing structural equation models. And I believe I give some examples in the code that I posted on the GitHub. Not sure we'll have time to get to that now, but it's certainly worth exploring. We have these tests of directed separation, in which case we've added the one between richness and distance back into the model. We only have one left. That was the non-significant correlation between the index of compositional heterogeneity and the index of the abiotic environment. And that gives us a p-value of 0.187. We do get this Fisher-C statistic and the global goodness of fit. You'll notice that the p-value is the same. That would be true if there's only one independence claim. There is also this chi-squared statistic. This is familiar for those of you who might have used the Lavon package to fit an SEM in the past. This is the default goodness of fit statistic that comes from that package. And thanks to Bill Shipley and Bob Duma's paper that came out in 2021, they've extended that to piecewise structural equation modeling. So we now have a second index of goodness of fit that we can report associated with our piecewise structural equation models. I should note that, and again, I believe this is in the example code, if you were to fit this model on the right, assuming complete linearity and nothing fancy, no different distributions, no nonlinearities, and so on, and you fit that model in Lavon, you should get the same chi-squared statistic and p-value as you get here. And again, I provide a worked example of that in the script that's in the GitHub repository. You get your coefficient output table, which should look very familiar, minus that standardized estimate column that we've discussed. And then finally, this is also, I think, important for diagnostic purposes. You get the individual proportion of the variance explained, or the R squared, for each of the endogenous variables in the model. And the reason this is included is because sometimes you can have a good fitting model, a good global fit, that actually is really poor for any kind of inference. And the reason being is that, well, those missing paths may be no different than 0. You might find yourself in a situation where the paths you've included are actually also no different than 0, probably because you have a highly underpowered model, you have a low sample size, so you can fit this SEM and you can get a good fit, but it actually ends up being really bad for making any kind of inference. And the R-squared is a nice check on this. It says, okay, you have these significant coefficients. To what degree are you explaining the variance in these responses as a consequence of these fixed effects? And I should note that for model classes in excess of LM, so I'll make a mention of this when we go back to the slideshow very quickly. These R-squareds or pseudo R-squareds can be extracted from GLMs, GLMMs, so if you have mixed models. It gets quite a bit complicated, and there's a number of folks who are working on deriving these valid R-squared measures from hierarchical models, mixed models, nonlinear models. The same actually goes for the standardized estimates, because there's some additional complexities that come when you move beyond just simple linear regression. And so I would just caution you to be aware that you may get these values back. You may see something here like conditional and marginal R-squared. And so it's worth taking a look at the help material and just making sure you understand what each of those is meant to represent. I'm going to go back to R here, or back to the PowerPoint very quickly. This is flying by. And just show that after our iterative process, we took our original hypothesis, we fit it. It did not match our data. We revised our hypotheses, refit the model. It had adequate fit. Ergo, we've now gone on to extract the coefficients from them, as well as the R-squared, and you can report them on the path diagram like this. And I would just note that the convention here is that the width of the arrow is scaled by the magnitude of that standardized effect, so that the larger the arrow, the stronger the relationship is between those variables. Again, because they're unitless, you can make those comparisons fairly between, say, this path, distance and abiotic, and this path, abiotic and richness, even if the raw variables are measured in very different units. As I also mentioned, the other benefit of SEM is that you can multiply adjacent paths, these standardized estimates, to be able to get a magnitude of these indirect effects. So for example, here 0.46 times 0.27 would be the effect, the indirect effect of distance on richness mediated by the abiotic environment. And you could actually compare that to the magnitude of the direct effect here, which is 0.37. So again, some really elegant understanding and nuanced understanding comes out of being able to build out these networked models. I mentioned this chi-squared statistic of goodness of fit. I just want to give you a very brief explanation on its background. In this case, we have a proposed model, and then we could fit something called a saturated model. This would be one that includes all paths in it. So in this case, we're missing only the path between abiotic and hetero. We can actually extract and sum the log likelihoods of each of these individual regressions for both the proposed and the saturated models. Take the difference, multiply by -2. That actually gives us a chi-squared statistic, which we can then compare to a chi-squared distribution to get our model-wide p-value. Again, very new implementation, which is really exciting. Brings it more into parity with the existing global estimation methods in Lavon. It's also important because you might have, say, a model that actually has identical paths, but you might decide instead to fit a different distribution or fit a mixed effects model, so include some random effects. And you would then be able to formally compare those using this likelihood-based chi-squared metric, which is something that would not have necessarily been possible with the tests of directed separation. That being said, those individual tests do give you important diagnostic information. For example, we saw that distance and richness were highly correlated, and significantly so in our data set, which led us to reintroduce it into the model. That's not necessarily information that would come out of this chi-squared statistic on its own. In Lavon, they have something called modification indices. I have yet to implement them in piecewise, but it's sort of superfluous because the output actually gives you both the tests of directed separation listed out individually, as well as the global Fisher C and the global chi-squared. So you get all this interesting information without having to go in and fiddle with individual tests. It's all presented for you in that summary argument. I had some other cool examples, but this is going a lot faster than I was anticipating. So what I'm going to do is just skip ahead and suggest some of the ways in which this piecewise implementation introduces benefits over that classical global estimation, SEM. As I mentioned, we can incorporate different error distributions. Often in ecology, we're working with count or abundance data. So we might fit a model to a Poisson distribution. We might be looking at survivorship, in which case we would model to a logistic regression, and so on. These are really, I think, it's the extension of SEM to these types of models that really attracted the attention of ecologists, because we are aware of the fact that the data we are collecting are not always or perhaps rarely normally distributed. So this gives us a lot more flexibility and power to honor the data generating processes that lead to the data that we observe or measure. I should also say that this piecewise framework can address non-independence in the data. So this could arise from things like pseudo-replication, that we can fit a mixed effects model, or we might have spatial or temporal autocorrelation. So we might fit a model with a defined autocorrelation structure. Those are all possible within the piecewise SEM package. And again, just treating the data more in line with how the data are generated. And most recently, we've extended the model classes to include truly nonlinear relationships. Formerly, this was through things like generalized linear models, which were linearized through the application of a link function, so a log link for something like a Poisson model. But now actually we can fit truly nonlinear functions in the form of generalized additive models and incorporate those into our structural equation model. I will say that the implementation of this is very new. It will work in some cases. It might not work in all cases, which is to say I'm still sort of figuring out all the usage cases and being able to address them. There's also some issues with how do you report the output from a generalized additive model in this path diagram graphical implementation. Those path coefficients are very nice. They have some nice properties, as we mentioned earlier, being able to multiply in order to get the indirect effects. However, when you have a nonlinear function, there's not a single number that necessarily reflects the relationship. So I have yet to see a very creative implementation of GAMs in path diagrams in the graphical implementation, but I'd be very open to exploring it. Or if anybody knows of any examples, I'd be happy to look at them. And I think that the real benefit of the piecewise package is that it's using familiar syntax in R, which is to say, if you're using these packages, if you're using the base package with LM and GLM, if you're using the NLME package or the LME4 package, or as of this weekend, the GLMM-TMB package, if you can fit a model in R, you can fit now a model in piecewise SEM, which is very cool. It's a little bit different from Lavon, because in Lavon, you simply code the equations. The underlying machinery is all the same. Here, you can fit a model as you always have, and then string them together using the PSEM function to build out that network and get some really interesting insight. I'm going to skip over this because I do want to leave time for questions. Please feel free to check out the script for both GLM and a GAM implementation and being able to test those different model structures against one another. Spoiler alert, the GLM and the GAM are less preferred than just the straight up linear implementation. Kind of interesting. I would just say that there are a couple of emerging topics in piecewise SEM and extensions that are familiar to users of, say, Lavon and the classical implementation. These include truly correlated errors, as well as latent variables. These are papers that are hot off the presses from Bill Shipley and Bob Duma. And so we would seek to implement those in the package, assuming I can find some time to do so. And I mentioned the full extension to nonlinear applications. How do we deal with the output from GAMs? A bit of an open question. And also, again, the great benefit of piecewiseSEM is that we have the flexibility to incorporate various kinds of model classes and functions within R. As I said, I added GLM-MTMB and support for models from the spatial reg package this weekend. Apologies that it's taken me so long. There's been lots of requests, but it's in there. And the sky's the limit. So I'd be very interested to hear what people would like to see implemented in R or in piecewiseSEM. I have even seen applications using distance-based matrix regression in an SEM context. That could be an interesting challenge to put into the piecewise package. And so please feel free to file a request on GitHub, and I will see what I can do. And finally, I appreciate your patience, especially those of you who've reached out about various bugs and errors. I try to make all the errors as informative as possible, but it can be hard, particularly when they stem from the functions for the model fitting, for example. But no software is perfect, and I do appreciate if you run into an issue that you log in GitHub or send me an email. You can see my contact information below, and a little reproducible example goes a long way. And finally, I'll just mention that I'm working on an open source resource, basically an electronic textbook for SEM. You can see the link here, which will go to a GitHub site that hosts all the chapters. It is a bit of a work in progress, although it's mostly there. And that will walk you through actually fitting SEM within both Lavaan and Piecewise, and is actually a testing ground for a lot of the functionality that I've been implementing over the years with worked examples and all the code. So I hope that will be a great resource. If you thought this presentation was interesting or you heard something that was intriguing, please feel free to check out the book. And I encourage you to think about SEM applications for your own data. So thank you so much. That was a bit of a whirlwind tour. I think we've got about 20 minutes left for questions. I'm happy to stay around past the half an hour. Thank you, everybody, for listening. And I will turn it over to Dennis, who is moderating the poll.
Hey, John, thanks. That was a great presentation. So if you're looking for suggestions of things to include in the package, there are a couple here in the questions, I think. Let's see how well we can do. There are many questions. I'll start from the ones that have been most voted. The first question is, can you incorporate time into SEM, for example, using repeated measures?
Yes, absolutely. And I mentioned you can do that through a number of different mechanisms. For example, you can fit a fixed correlation structure like an autoregressive AR1 type structure to reflect the fact that you have taken measurements sequentially through time. Mixed effects models are also good for handling those. And you may actually feel compelled to code your different time steps as individual variables within the model. That actually improves your capacity to infer causation, because necessarily time marches forward. And so you have a staggered relationship between the cause potentially and the effect. So there's a lot of different ways to be able to incorporate that. And I believe there should be some examples in the textbook too. So check out that link.
Yeah, and I think this probably speaks also to the second question, because it is asking if it's possible to include as part of a SEM cyclical relationship between variables. So in your example, it would be the case of ecological community influencing the abiotic factors rather than the other way around. I guess the answer would be through times, like you're saying.
So graph theory forbids these sort of like cyclical A leads to B, leads to C, leads back to A, because it's just not possible to fit and derive truly independent effects of, say, A on B, having removed then the effects of C on A, given the cyclical nature of the diagram. The Lavaan, the classical implementation, it is possible to do that. And fit sort of bidirectional relationships as well. It is very difficult, and it requires a very specific kind of model structure. So that may be something to investigate if you're interested in looking at those questions. But otherwise, I would say piecewise is probably not sufficient for those needs. That being said, one compromise could be to actually fit different models with different directions. So like classic top-down versus bottom-up, right? And you could actually then use something like AIC to formally compare the two to ask which configuration is more likely. Is it more likely that it's going from bottom to top or going from top to bottom? And that could be one way to get at this question of sort of bidirectional relationships within SEM without breaking the underlying theory.
What about the other idea of having, say, the ecological community and one time step influencing the abiotic factors at another time step? So having kind of this bidirectional relationships, but separated through time, and then you can perhaps help tease those things apart.
Yeah, that would be a perfectly reasonable implementation, as long as you are sure never to have arrows going back through time. If you do, let me know. I would love to know the secret to time travel.
All right. The other question is, can categorical variables be used within SEMs?
Yes. The short answer is yes. The long answer is we have implemented a way to be able to include categorical predictors as within the piecewise SEM to be able to get coefficients or at least significant tests and marginal means predicted from those. There is also an extension of structural equation modeling called multi-group analysis, in which case you would fit the same model structure, but to different groups within your data. So you might have something like, fertilized versus unfertilized. And so you could then parse your analysis and look at the relationship between your variables under one set of conditions versus another set of conditions, and actually then formally compare the pathways in each of the individual pathways within your SEM to be able to ask, do they actually differ by these different groups, these different levels of this categorical variable, or are they in fact the same regardless of whether you're in group 1 or group 2? And there's a chapter on that in the ebook, so if that's of interest to you, please check it out. And it also talks about how to better deal with categorical variables, maybe some tricks on how to code them, some tricks on how to interpret the output from the summary function, and so on. I'm just looking to make sure that's true. Yes, there's a whole chapter on multi-group analysis and actually a whole chapter on categorical variables. So hopefully this would be really, really useful. I'll go ahead and put this link in the chat too.
Great. And is multicollinearity a concern when you're fitting SEMs?
Yes, this is a really important point, which is that you have to satisfy the assumptions of the individual models that you're fitting. So generally speaking, normality of errors, homogeneity of variance, independence among your predictors, or at least to a reasonable degree. So if you do have two highly correlated predictors, you're going to have the same consequence in your SEM as if you were fitting them in a simple or multiple regression context. So it's important to be able to examine the assumptions of each of your models, and you can run something like variance inflation factors to try to see whether collinearity is an issue. Again, one of the nice things is you can build your models outside of the PSEM function, do all this diagnostic work, and then once you're happy with the model and you feel like it meets your assumptions, pop it in the SEM, and you'll be good to go.
Yeah. And what about interactive effects between predictor variables? Does SEM accommodate those or not?
So again, short answer is yes. We can encode, or you're welcome to code interactions within your models. Everything will be estimated. You'll actually also get a standardized estimate, which is pretty cool. I believe, and I would have to go back and double check this, but in those tests of directed separation, so when you're evaluating your model fit, it's not always clear whether you would expect the interaction to propagate through the network, which is to say, you include an interaction predicting something because you have some strong suspicion that there is an interaction there for that particular variable. It may not be that the variable that's 2 or 3 variables downstream is also expected to respond to the interaction between those 2 variables. So I think the one caveat is that in investigating those independence claims, I believe the decision was made to not propagate the interaction through in those tests. So just be aware of that. I'd have to double check. But you're perfectly, I mean, you can fit them, sure. It's just with all interactions, whether they're in an SEM context or not, it's just worth thinking about, is this necessary, particularly when you get past 2-way interactions and start getting into the realm of 3- and 4-way, can I actually interpret these, and how might they fit into a network context?
One of the questions has to do with the required sample size when you're trying to fit a SEM to your data. Are there rules of thumb regarding what the sample sizes ought to be?
Yes. This is a great question, actually, and something I probably should have put in the benefits of piecewise. So with global estimation, you need enough power to be able to fit that entire variance covariance matrix that includes every variable. With the local estimation, with the piecewise package, you really only need enough observations to fit any individual model. And so that somewhat relaxes the assumption, or somewhat relaxes the necessity for a high sample size. However, you might find yourself then in a situation where you have a very underpowered model. So that gets into that situation I had described where you actually get this paradox, like a paradox where your model actually fits the data very well, but then nothing within the model is actually significant. So it's somewhat useless for inference because your missing paths are no different than 0. So your goodness of fit is very good, but then your included paths are also no different than 0. So Jim Grace has come up with something called the D rule, where he suggests that you should have a sample size of basically 5 times the number of variables, observed variables in your model. So in the Keeley example, there were 4 variables. He would suggest a minimum sample size of 20 then to be able to fit that entire SEM.
Yeah. And I think somewhat related to this, one of the questions has to do with the R-squared values for the 3 equations were somewhat small. I think 0.12, 0.21, 0.47. So how confident can you be on the interpretations that you make if in none of these models you explain the majority of the variability in the response?
This is a good question, and I wouldn't say it's exclusive to SEM, right? And this comes down to how comfortable you are with reporting models that might have a low proportion of explained variance. There was a meta-analysis that's probably 10 or 20 years old now that suggested like the average R-squared across ecological studies was like 0.04, which is very low. I think it just serves to demonstrate that we work with messy systems. But another important thing is that, partly thoughtful construction of the path diagram improves your capacity to speak to causality, as I mentioned. If you have a very low R-squared, it might imply that there's a large proportion of variability in your responses that's not explained, and therefore you might be missing something important in your model. So that's maybe another tool to use to go back and say, okay, I saw a significant relationship between distance and richness. I only explained 12% of the variance. Maybe there's something else out there that explains richness, temperature or precipitation, or some aspect of the environment that wasn't captured in those other predictors that would be worth including in the model. And then it might be that the relationship that you had seen previously is no longer significant. Maybe it was reflecting an environmental gradient rather than a spatial one. And so that's an important step towards ensuring that you can actually speak to the causal associations rather than just potential spurious correlations.
And I think this one is really interesting. It's what is or are the biggest mistakes people make when when they're running piecewise SEMs? What has been your experience with that?
That's a great question. So I would say the big mistake, or at least the temptation I think most people when they first do it would arrive at, is how to interpret the goodness of fit statistics and the p-values that are associated with them. So I mentioned that in this case, we actually want a high p-value because that implies that the correlations in your data are generally captured in the structure of your model. You're not missing anything really important. And I think there's always a temptation in ecology to go for the lower p-value. That means it's significant. Significant is good. And so I have seen publications, I won't call anyone out, where they got a really low p-value on the model and they said, yeah, this model's great. And the reality is, of course, that it's implying there's something missing, some associations in their data that aren't present or specified in the paths. So probably they should have gone back and included those, or otherwise reevaluated the structure of their model. I would say the other thing too is the temptation to break down every predictor. So I mentioned in the beginning, like the species richness was predicted by both the abiotic index and the compositional heterogeneity index, and that we actually want both of those to go into the same regression. We don't want to model each of them separately from one another because we want those partial effects to come from the model that we can report.
And in terms of wish list of things that people might perhaps want to have to see in the package, there's a question here if you can input as one of the models that are part of the SEM, if you can use Bayesian models like BRMS inputs.
Yeah, I do get this question, and it will show my ignorance of Bayesian methods. I mean, a lot of what I've talked to you about today is really driven heavily by traditional inferential statistics, p-values, and the like. I don't foresee any issues, but philosophically, I'd have to sit down and mechanically, I don't foresee any issues. Philosophically, I would have to sit down and think about whether those are compatible. I'm sure somebody here is already done it and thought more deeply about it than I have. And so feel free to put it in the chat. I'm sure there are probably examples in the literature using SEM and Bayesian statistics.
Yeah, and well, we are almost out of time. Just I think the last question here is, can the available models in piecewise SEM include offset variables, say, to account for detection probability of a species in bird surveys? Perhaps you could use detection offset, a detection offset variable.
I don't believe so at the moment. The inclusion of functions within the model formula has been a sticking point here. For example, transformations, scaling, offsets, and so on. The other issue that has sort of perennially bugged me is using a 2-column response of like successes and failures in a GLM context. So that is something that I'm looking at incorporating, particularly now that we have a bigger suite of functions within formulas that arise from the inclusion of GAMs, and it will be necessary to be able to properly handle all of those. So to that person, I would say, thank you for your patience again. Definitely something that's on the list, and we're working towards it. Can I make one final comment, Dennis? I just noticed somebody said in here, is SEM always a good alternative to traditional linear models? And I would just end by saying the old quote, when you have a hammer, everything looks like a nail, which is to say SEM is super powerful. I think it's potentially game changing in terms of the insight you can achieve from your studies. But I mean, it's not in every single one of my papers, because it's just not always necessary to be able to get the answers that I'm interested in. And the same, I think, is true for a lot of ecological studies. So I would say, if you have questions where you have these networks of hypotheses that you want to be able to evaluate, you have a potential for these indirect or cascading effects, SEM is a perfect tool. If you're just looking at a classically designed blocked experiments, two-factor ANOVA, that's probably sufficient. And it may not necessarily be the case that you need something as sophisticated as SEM. So I would just say, like with every statistical method, it can be awesome and a game changer, or it can be completely superfluous and, simpler is better. And it will be up to you as the investigator really to make that determination. And probably reviewers.
Yeah, great way to finish the presentation. So I appreciate you preparing this very thoughtful presentation and taking the time to answer all these questions. Unfortunately, we were not able to go through all the questions, but just the sheer amount of them just shows how interested people are on this topic. So that's fantastic. And again, because this is being recorded, I hope that this can be a useful resource for anybody that wants to revisit this and learn about how piecewise-SEM works. So thank you very much, Jon. Yeah, go ahead.
Just one final thing. Thank you so much, everybody. And please feel free to reach out if you have questions or we'd like more resources to be able to learn more. I would be happy to provide them.